Welcome to AI Paper Slop. If you're building robot foundation models, you know tactile feedback is the holy grail. Today we are tearing into a paper titled TouchWorld, a predictive and reactive tactile foundation model for dexterous manipulation, published July 10th, 2026 by researchers from Harbin Institute of Technology and Finese AI.
Yeah, this one is, it's a really fascinating read.
It really is, and we are diving straight into the core insight here. State-of-the-art vision language action models, or VLAs, they consistently fail at contact-rich tasks. And they fail because they couple slow semantic reasoning with fast contact feedback in a single monolithic control loop.
Right, exactly.
So TouchWorld solves this bottleneck by decoupling these timescales into a predictive and reactive hierarchy. We're talking about a 1 Hz semantic planner that predicts tactile goals, a 10 Hz Visuo-Tactile policy for nominal action chunking, and a 30 Hz residual transformer for real-time local tactile correction.
Which is, a completely different way to structure the architecture.
Definitely. So the central question we are asking you today is this: can explicitly separating semantic planning from high-frequency tactile reflexes finally give robots the physical common sense they currently lack?
Well, to really appreciate the scale of this problem, we first need to look at the massive gap between what current models can think about and what they can actually physically touch.
Right.
We're looking at top-tier systems out there right now, models like Pi 0.5 or GR000T N1.7, These models have phenomenal semantic understanding.
Oh, absolutely.
They can navigate an unstructured room, they can spot a coffee cup in the middle of a ton of clutter, and they understand really complex natural language instructions.
Yeah.
But the second you ask them to execute a task requiring continuous physical contact like wiping down a table or inserting a really tight power plug, they just fumble it completely.
Right, because standard VLAs handle the actual sensation of touch terribly. I mean, when you look at the architecture of a standard VLA, the engineers essentially just take the incoming tactile sensor data, format it as an additional stream of input tokens, and just dump it into the exact same transformer model alongside the visual data and the language prompts.
Exactly, which forces the entire system to process the physical sensation of touch at the exact same rate it processes a high-level language command.
Right.
And when you map that onto the actual physics of manipulation, it just causes catastrophic failures, like understanding an instruction like water the flower and deciding to reach for the spray bottle. That's a semantic reasoning process.
Sure.
It evolves slowly. You don't need to update your understanding of the phrase water the flower 30 times a second.
Right. That would be a waste of compute.
Exactly. But physical adjustments, like actually feeling the hard plastic of the spray bottle starting to slip from your gripper or, regulating the force of your fingers so you don't crush it, those require rapid, high-frequency reactive processing.
Yeah, I was actually thinking about this architecture, and the standard VLA approach is basically like a human trying to play a hyper-fast competitive video game, but their brain's high-level strategic planning and their fingers' twitch reflexes are forced to run on the exact same slow processor clock speed.
Oh, that's a great way to put it.
Right,
Yeah.
like you'd see an enemy on screen, you'd know exactly what strategy to use, but because your fingers have to wait for the slow strategic brain to finish computing the overarching game plan before they can even move, you've already lost the engagement. Your reflexes are just completely bottlenecked by your strategy.
That is exactly what happens, and the paper proves this bottleneck exists in the current baselines. They benchmarked against these monolithic tactile policies like FTP1.
Right.
And in contact-rich tasks where friction and force are changing by the millisecond, like sliding a tight object into a slot, those monolithic models struggle immensely because they are forcing slow reasoning and fast reaction to share the exact same model capacity and the exact same control loop. So the model might produce a trajectory that looks visually perfect from a distance, but the moment it makes contact, it fails. It literally cannot process the tactile slip and calculate the grip correction fast enough before the object just drops to the floor.
So if forcing everything through a single processing loop is the big bottleneck, the paper solution is to shatter that loop entirely.
Shatter it completely. Yeah.
So TouchWorld introduces this multi-timescale hierarchy that breaks the robot's brain, so to speak, into 3 distinct time-specific layers. At the top, you have the high-level planning layer operating at a really slow 1 hertz.
Right.
In the middle, you have a Visuo-Tactile goal-conditioned policy layer running at an intermediate 10 hertz.
Yep.
And at the bottom, you have the Reactive Tactile refinement layer running at a fast 30 hertz.
And breaking it down by frequency is, that's how biological systems work too.
Yeah.
The 1 hertz layer handles the slow semantic updates, so the long-term goals. The 10 hertz layer handles intermediate action chunk generation, like the broad sweeping movements. And then the 30 hertz layer provides real-time contact correction, which is the immediate physical reflexes.
I do want to push back on this architecture complexity a little bit, though.
Sure, go ahead.
Why strictly 3 layers? I mean, if the goal is just to separate the slow, high-level reasoning from the fast, low-level reflexes, wouldn't a simple 2-tier system be enough?
You mean just skipping the middle?
Yeah, exactly. You could have a slow, high-level vision language model acting as the strategic brain, and then a fast, low-level policy acting as the reactive muscle. Why inject this middle 10 hertz layer for nominal action chunking? It feels like an unnecessary middleman that just, adds latency.
I get why it looks like that, but that 10 hertz middleman is actually doing the heavy lifting for navigating the physical geometry of the world.
Oh, really?
Yeah, without it, you have a massive translation gap. So a 1 hertz semantic plan might just say, move hand to the cup, but a 30 hertz tactile reflex only knows how to adjust finger pressure based on immediate contact. Neither of those layers knows how to smoothly move a robotic arm through 3D space to get from point A to point B without, smashing into an obstacle.
Okay. That makes sense.
That is what the 10 hertz layer does. The researchers use a technique called flow matching to generate what they call a nominal action chunk over an action horizon of H72.
Okay, let's ground that term for a second for anyone listening. When they say they use flow matching for an action horizon of H32, what is the robot actually computing in that exact moment?
Right, so flow matching is this generative modeling technique that basically transforms a simple known distribution into a complex data distribution. So in this case, complex physical trajectories.
Got it.
And when they set the horizon to H32, it means the 10 hertz layer is looking ahead 32 steps into the future.
Oh.
Yeah, it evaluates the visual layout of the room, calculates the physics, and plots an optimal, smooth path through 3D space. It generates the nominal trajectory, which is at the best guess at how the arm should move, assuming nothing goes wrong.
Okay, so it's charting the baseline map. Because if you just jumped from the 1 hertz grab the cup command directly to a 30 hertz finger reflex, the arm would just flail because the reflex layer doesn't understand the geometry of the room at all.
Exactly. It would have no idea how to navigate.
Right. The 30 hertz layer isn't generating the movement toward the cup. It relies entirely on that 10 hertz baseline map, and it only steps in to make micro adjustments if the map fails upon physical contact.
Which means the system is incredibly efficient. The 10 hertz layer handles the geometry, leaving the 30 hertz layer completely free to dedicate all of its processing power exclusively to immediate, localized pressure changes.
That's super elegant. So let's zoom back up to the top of that hierarchy, that slow 1 hertz high-level planning layer. This is where TouchWorld generates its long-term goals before the robot even twitches a motor, and the mechanics here are wild to me.
Yeah, they really push the boundaries here.
Right. It contains 2 main components. First is the subtask planner, which they adapted from Qwen 3 VL4B Instruct. It takes the messy human prompt, looks at the robot's memory of what it just did, and outputs an executable subtask. So a vague prompt like water the flowers gets decomposed into a concrete phase like pump the sprayer.
Yeah, and that subtask generation is, it's fairly standard for modern VLAs.
Yeah.
But the second component in that 1 hertz layer is where this paper takes a massive leap.
The Tactile World model.
Yes. They took a massive video generation model, 12.2 TI2 V5B, and fine-tuned it.
A 5 billion parameter model just for this.
Exactly. It takes the current visual observation of the room and the new text subtask, and it actually generates a 17-frame visual tactile clip at 384 by 224 resolution.
That is insane.
It is quite literally forecasting the future contact outcome before the robot even begins to move.
So it's hallucinating a video of itself successfully completing the task. But, using a 5 billion parameter video generation model to predict a 17-frame clip of tactile subgoals, that sounds incredibly computationally heavy for a robot that needs to operate in real time.
It definitely sounds heavy, yeah.
Right. Is hallucinating the feeling of a successful grasp actually driving better physical execution on the robot hardware? Or is this just, burning compute to look impressive on a benchmark?
It's a valid concern, but the researchers ran extensive ablation studies to answer that exact question, and the data shows it's absolutely critical for execution. That tactile world model achieved an 86.3% temporal contact accuracy.
Okay, which is high, but what are we comparing that against? Like, what's the baseline?
They compared it against a nearest neighbor retrieval baseline.
Okay.
A nearest neighbor approach is much cheaper computationally.
Okay.
The robot essentially looks at its current situation, searches a database of its past experiences for the most visually similar moment, and just assumes the tactile outcome will be exactly the same.
Right, just pulling from memory.
But that baseline only hits 77.5% accuracy. It fails when the robot encounters a novel situation or, even a slightly different object orientation. By actually generating a novel 17-frame prediction, the tactile world model provides a vastly superior, highly accurate target for the downstream 10 Hz policy to aim for.
And what happened when they removed that hallucinated goal prediction entirely?
When they forced the policy to rely only on the current observation and the text subtask, the model's contact-aware action generation just degraded severely. The overall success rate plummeted.
Wow, so it really needs that anchor.
It proves that providing the lower layers with a highly accurate generated forecast of what success should look and feel like is a required reference point.
Interesting.
And regarding the compute cost, because you brought that up, they actually instituted a really smart gating mechanism.
So.
The world model doesn't run continuously at 1 Hz. It only fires and generates a new 17-frame clip when the subtask planner indicates that the task phase has changed.
Oh, I see.
So if the robot is in the middle of a stable motion, it just reuses the previous prediction, which saves a massive amount of processing power.
That makes total sense. Okay, so the 1 Hz layer predicts this perfect, hallucinated 17-frame future where the robot grasps the spray bottle flawlessly. But any ML engineer knows that physics is messy.
Very messy.
The world model predicts perfection, but what happens when the spray bottle has, condensation on it and it starts to slip in real time? That 1 Hz planning loop is way too slow to save it. The bottle will hit the floor before the semantic planner even finishes its next processing cycle.
And this is exactly why the bottom of the hierarchy exists, the 30 Hz reflex, officially called the Tactile Condition Refinement Policy. They implemented this as a tactile residual transformer, or TRT.
I really want to break down the mechanics of this TRT because this seems to be the engine of the entire paper. It operates using a sliding window mechanism, right?
Yes.
It looks ahead at a nominal action window, which they set to W16.
Right, so it is looking at the next 16 steps of the trajectory that was generated by the 10 Hz middle layer.
But it doesn't just blindly follow those 16 steps. It also pulls in the robot's proprioceptive histories, meaning, where all its physical joints are in space right now and what they've felt over the last fraction of a second.
Exactly. It's immediate reality.
Right. And based on that immediate physical reality, it predicts a residual action window. And the paper notes that it operates in a 58-dimensional tactile sensitive action subspace.
Yep, 58 dimensions.
Which sounds incredibly abstract. I mean, we live in a 3D world. What are those 58 variables actually mapping to on the physical hardware of the robot?
I know it sounds dense, but it's really just mapping the anatomy of the end effector. They aren't trying to calculate adjustments for the entire robot.
Okay.
They completely ignore the wheels, the torso, and the shoulder. Those 58 dimensions are exclusively focused on the parts of the robot interacting with the physics of the object.
So just the hand and wrist.
Exactly. You have the 6 degree of freedom pose of the wrist, so your XYZ coordinates plus pitch, yaw, and roll.
Yeah.
Then you have the intricate joint angles of the dexterous hand itself, and the multidimensional readings coming directly from the tactile sensors on the fingertips. The TRT is only calculating adjustments for that highly specific 58 variable subspace.
That's fascinating.
And once it calculates the necessary correction, it commits to a short burst of actions, they say C4 actions, before it refreshes the data and calculates the next residual based on the new sensor readings.
Okay, so to put this into a workplace analogy, the 10 Hz Visuo-Tactile policy is like the project manager drawing the overarching plan on a whiteboard.
I like that.
They map the path. But the 30 Hz TRT is the worker on the factory floor, literally holding the wrench. The worker is making the high-frequency micro-adjustments to their wrist and fingers so the part doesn't snap under pressure.
And if we carry that analogy forward, the project manager doesn't need to know exactly how hard the worker is gripping the wrench. They just need to know the pipe is being installed.
Right.
That's why emphasizing the word residual here is so critical. The TRT is not calculating a whole new path for the arm. It is calculating the mathematical difference, the residual, between the nominal action drawn by the project manager and the required high-frequency action needed to not drop the pipe.
Oh, wow. So it's just doing the math on the delta.
Exactly. By constraining the target to just that difference, the architecture forces the refinement policy into a strictly local role. The 10 Hz policy worries about getting the hand to the goal, and the 30 Hz policy just adds or subtracts a tiny bit of force to keep the item stable based on local pressure changes. They don't fight for control over the arm.
A perfectly decoupled hierarchy, like this sounds incredible on paper, but the reality of training it sounds like an absolute nightmare.
Oh, it is.
If you try to run end-to-end backpropagation on a system that spans a 1 Hz 5 billion parameter video model and a 30 Hz tactile reflex loop, the math is just going to fall apart.
Oh, completely.
You'd be trying to flow error signals from a dropped cup at 30 Hz all the way back through a generated 17-frame video clip. You get massive instability, vanishing gradients, the whole system would just crash. So how do they actually train this thing without it breaking?
Well, they avoid end-to-end backpropagation entirely.
Oh, really?
Yeah, instead, they designed a 4-stage training pipeline to keep the timescales completely separable. Stage 1 trains the subtask planner to get the semantic updates right. Stage 2 fine-tunes that massive tactile world model on 10 hours of human tele-operated robot demonstrations, teaching it to predict those visual tactile clips accurately.
Okay, so they do the top layer first.
Yes. Then Stage 3 trains the 10 Hz nominal VLA policy to chart the geometry.
And then Stage 4 is where they train the reflex.
Yes, and this is the crucial part. In Stage 4, they train the TRT on high-frequency residual targets, but they completely freeze the 10 Hz VLA policy.
Oh, yeah, they freeze it.
By freezing the policy, the TRT is forced to only learn the high-frequency differences, the residuals, without corrupting or overriding the nominal path planning that was already established in Stage 3. It isolates the variables perfectly.
That solves the software side of the training, but what about the hardware? I mean, gathering 10 hours of dense tactile demonstration data requires serious physical setup.
Oh, they spared no expense. They used a MetaQuest headset for immersive visual feedback for the human operator.
Wow.
For hand tracking, they combined MetaQuest Touch Plus controllers with a Wuji glove. And on the actual robot executing the tasks, they used Wuji dexterous hands equipped with JQ Industries tactile gloves to capture that dense contact observation.
So it's a highly pristine, cutting-edge teleoperation pipeline.
Very much so. And they used it to establish a benchmark of 6 contact-rich tasks. We're looking at things like power plug insertion, pot wiping, and tissue pulling. These aren't tasks where you can just grasp an object and move it right. They demand continuous, closed-loop tactile awareness.
And the results they achieved on these tasks are staggering. They had a 65.0% clean success rate. But more importantly, they had a 53.7% success rate under active human perturbation, meaning a human was actively hitting the robot's arm and messing with the objects while the robot tried to work.
Which is wild to watch.
It is. And that 53.7% success rate beats the strongest baseline model, FTP1, by a massive 18.5 percentage points.
Surviving active perturbation is, frankly, the ultimate test of a robotic control loop. It means the system isn't just memorizing a path, it's dynamically reacting to physical reality.
But I have to play the skeptic here. Whenever I see an 18.5 percentage point leap over state-of-the-art in robotics, I have to ask, how much of this success is just because they bolted a fancy JQ Industries tactile sensor onto the robot versus the actual multi-timescale architecture doing the heavy lifting? Is it the hardware giving it a better sense of touch, or is it the math?
It's a totally fair question. I mean, the hardware is a prerequisite, obviously. If you completely remove the tactile input, performance drops across the board because the robot is essentially numb. Yep. However, the researchers ran a highly specific ablation study to answer exactly that question. They kept the JQ Industries tactile sensors active and feeding data into the system, but they removed just the tactile residual refinement layer, that 30 Hz TRT.
So the robot can still feel the touch, but it loses its reflex loop. What happened?
It completely destroyed the model's ability to handle the human perturbations. The performance in the perturbed setting plummeted from 53.7% down to 40.3%.
Wow, just from losing that one layer.
Think about what that means mechanically. The robot still had its high-level semantic plan, it still had its 10 Hz trajectory, and its sensors were still actively sending tactile data. But without that dedicated 30 Hz local loop to process that data instantly and calculate a residual adjustment, the data just had nowhere to go in time to matter.
Right.
By the time the slower layers realized the object was slipping because the human bumped the arm, it was too late. This ablation proves definitively that the reactive architecture, the math itself, is what gives the robot the ability to actually utilize the hardware and recover from active disturbances.
Ultimately, TouchWorld proves a vital point for anyone building in this space. Scaling up robot foundation models isn't just about feeding them more and more video data to build massive visual brains. It is about deeply respecting the different timescales of human-like cognition and reflex. You simply cannot solve a millisecond physics problem with a 1-second semantic reasoning loop. The architecture has to reflect the physics of the environment it's operating in. We spend so much time discussing scaling laws for vision language models, but this paper forces us to ask, what are the scaling laws for tactile residuals? If future datasets can capture enough diverse, high-frequency physical interactions across different materials and forces, could a generalized residual transformer become a universal reflex plugin? Imagine a standalone TRT module that you can just attach to any robot arm, instantly giving it an innate, zero-shot sense of physics, friction, and slip recovery, operating entirely independent of whatever high-level semantic brain you have driving it.